Hi, it's Michael Litsky with another physics video. Today we're going to look at a really tough pendulum problem. I hope you're never in a class where you get a problem this tough, but I had a student who did, so here is how you work out a pendulum driven not by gravity but by a spring pulling at it. So here's the setup. We've got a wall, and attached to the wall by a spring with spring constant K is a thin rod. That thin rod is pivoted not at the end, but at a distance r from one end. The entire length is L. Don't you hate these problems where they don't give you any numbers? It's all just letters. And the mass of the rod is M. And the idea is that this is a pendulum because when you pull it out away from the wall like this, then the spring is going to pull it back. Boing, but of course it will overshoot and go in towards the center, and then the spring pushes it back, and so it goes boing, yoing, yoing, yoing. And of course the sound effects are critical. And it's a pendulum. It's a physical pendulum. Our job is to show that the period, actually the square of the period, for which we usually use capital T, the square of the period is 4 pi squared times the mass of the pendulum over 3 times the spring constant times r squared. Remember, r is the distance to the pivot. And then all that times L squared plus 3r squared minus 3rl. How to do it? Well, the first thing we might do is to look up physical pendulums in our text and find that for a physical pendulum, the period is given as 2 pi times the square root of the moment of inertia of the thing that's swinging divided by mgd. And at least we can recognize that this equation is just the square of the pendulum equation. So if we can show that the 4 pi squared square rooted is 2 pi, so leaving out the 2 pi and all that, we need to show that this is what we get in place of this. Now, I have to confess to you, I could not have solved a problem like this when I was in high school or even in college. Since I see what the answer is supposed to be, I can sort of work backwards and quick talk my way into the reasoning behind why it would be so. So follow me in the following arguments, but don't feel bad if you didn't think of it yourself. So we want to look at this I over mgd. I is the moment of inertia for a rod pivoting around something that's not its center but not its end. So let's see. We've got a thin rod and it is pivoted a distance r from the end. So we look at all of our formulas for the inertia of a thin rod, and we find that if it was pivoted at the end, we'd be fine. We would have 1/3 ml squared. If it was pivoted in the middle, at the center of mass, it would be 1/12 ml squared. But we're sunk. We don't have a formula for a thin rod that's pivoted a distance r from the end. But wait, there is the parallel axis theorem to the rescue. And you remember that says that the inertia is the inertia about the center of mass, which we do have, that's this one, plus mr squared, where r is the distance from our pivot point to the center of mass. And let's see, there is our pivot point right there. Center of mass would be about here at L over 2. So this distance that we want, this distance here, is r minus L over 2. All right, we should be able to do it then. The inertia is 1/12 ml squared plus m times r minus L over 2 quantity squared. And it's now a bit of messy algebra to work that out, so I'll do it in quick little chunks here. Here's where, if you've memorized that squaring a binomial formula, you're in good shape. R squared minus 2 r L over 2 plus L squared over 4. And that we can factor out the m and factor out the 1/3 so that we put the m over 3 in front. And what's left inside is L squared plus 3r squared minus 3rl. And if we compare that to what we are supposed to get, m over 3, L squared plus 3r squared minus 3rl. So if we could just get the mgd in the denominator to be kr squared, we'd be sitting pretty. But mg, the force, for a spring, force is minus kx. And I'm afraid that here is where we're going to have to look under the hood. We're going to have to get our hands dirty on the differential equation that leads to this simple formula. All right, let's review where the formula came from for a gravity pendulum. So we have some shape that is being pivoted at the center of mass, being pivoted a distance d from the center of mass, and the force that's pulling down is applied at the center of mass, and it's mg. So if I put the mg vector and the d vector tail to tail, then the angle between them is theta, and the torque of the rod, or whatever it is that's being pivoted, the torque is the force times the distance times the sine of the angle between them, the smallest angle between them. Hope you enjoy my cat walking through the video in the background there. So in this case, for the gravity pendulum, the torque is mg d sine theta. And then we use the rotational equivalent of F equals ma, except its torque equals I times the angular acceleration. And the torque, we just said, was mg d sine theta equals I, and the angular acceleration is the second derivative of theta with respect to time. Now here's where we do what always used to look like cheating to me. When theta small, sine theta is just about equal to theta itself. So we put in the mgd theta equals all that stuff, and we have a differential equation. And without going into the details of solving that differential equation, the solution is a cosine function, and the period of that cosine function, in order to make that differential equation work, the period has to be 2 pi root I over mgd. So we want to come up with the equivalent for our spring pendulum. Here's our spring pendulum. We got our rod. I'm swiveling it now so it's facing the same direction, but there's no gravity involved. It's still just going wang, 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 wang. Here's the pivot, and here's the I'm just going to draw an arrow for the force of the spring. And that would be kx, where k is the spring constant and x is how far it was displaced. And we still imagine it pulled out a distance theta. So, but here's the problem. First of all, the force is not being applied at the center of mass like it was with gravity. It's being applied at the end. And when I put those two vectors tail to tail, there's the kx vector, the force. There's the r vector, the distance from the center, from the pivot to where the force is being applied. There's our angle theta, but oh dear, we've got this extra pi over 2. So our force, our torque in this case, is kx r times the sine of pi over 2 plus theta. Well, all right, we've got something, but we can't have x in our final formula. And also, even worse, when theta is small, sine of pi over 2 plus theta becomes just sine of pi over 2. And the sine of pi over 2 is 1. So that's just kxr. And that's nothing like what we're supposed to come up with. But here's the last little trick. If we look at a right triangle made up of, there's x, there's r, there's theta, x is r sine theta. Work it out if you don't believe me. And so our formula actually becomes that the torque is k r squared sine theta. And that we can replace with k r squared theta when theta gets small. And then if we went through all that business of plugging it into the differential equation and solving, we would have a solution, which was a cosine with a period of 2 pi root I, this time over k r squared. Oh yeah, we got it, because when we plug in that inertia that we had before, that inertia over kr squared puts the kr squared in the denominator, square rooting that, 2 pi, that's the period, and then if we square everything, we get the formula we were supposed to arrive at. But boy, what a lot of work.